Welcome everyone. This is our 27th live stream geometry. We have 3 other people here so far with us. And today I'm going to go through problems from the Middle European Math Olympiad. So I'd never heard of this contest until just a couple days ago, but it has a very large amount of problems that look really good. So I'm going to do some of them this session, but there's enough that I think I could keep doing them for maybe 1 or 2 more sessions. So with that, I will share my screen. Hold on just a second. It's a competition between 10 different countries. So it started with just Austria and Poland, but now there's 10 different European countries that participate, and it's every year. There's both a team competition and an individual competition. So I took problems from both. And it's a very kind of similar format to the IMO. It's each contest is 5 hours each day. All right, so here's the first problem. So we have a right triangle. You guys can all see it, right? We have a right triangle with right angle at B and circumcircle omega. So let me draw it like this. All right, and then where's my? I'm just gonna try to cheat here. Whoops. That's called a C. And D is the midpoint of arc AB. So yeah, obviously we know triangle ABC is inscribed in a diameter. Okay, so I'm going to take the perpendicular bisector of AB. Well, actually, I think I'm going to want to make B over here instead. You'll see why I'm just like. So we want P to be such that CP is equal to CD. Okay. And P is on AB. So this is P. And then, okay, so CPD is isosceles. And then X is on the circle such that AX, X and Y are in the circle such that AX is equal to AY is equal to PD. Where's my compass tool? There we go. And we want to show that X, Y, and P are collinear. It's kind of random, but interesting. All right, so I'm going to hide the circle for now. So AX equals AY is equal to PD. It almost looks like AX and PD are parallel, so I'll move the diagram a little bit just so I don't think that's true. AX and PD shouldn't be parallel, but it's saying X, P, and Y are collinear. Maybe you can show the powers of P with respect to these circles are equal. So which PA? Let me draw this circle. Let me draw these, unhide these circles. So it looks like that's actually tangent. Looks like XY is tangent to the circle. So PA times, yeah, basically, yeah, we want to show it lies on the radical axis. So if we can show PA times PB, that's the power of P with respect to this circle, and then PA squared minus PD. Yeah, I like that. So let's see if we can do that. So yeah, we don't know yet that these are collinear, but let's, okay. So PA times PB So yeah, how do we get PA squared minus PD squared? I'm just thinking. But yeah, it's interesting that those circles are tangent at point P.
They are not really tangent at P if you just shift the diagram a little.
Oh wait, so oh, they're not actually tangent. It just looked like it. Yeah, you're right.
For them to be tangent, P had to lie on AO.
Oh yeah, no, you're right, because they're both symmetric across the line AC. Interesting. Okay. So yeah, we want to show the powers are the same. Maybe we could use Casey's theorem. That would be a little tricky here.
Maybe due to different angles and lengths being interchanged, we can try using sine law or something. There are not any degrees of freedom here. Sine law should be enough, I guess.
Maybe drop a perpendicular from D to AB. Yeah, I keep forgetting that D is the midpoint of arc AB, right? We have to use that. So if E is the midpoint of AB, so that's the same as the perpendicular. So yeah, the power of P with respect to the circle is PA squared minus PD squared. Let's see, PA is, yeah, we have to use some of these right angles too. So if we rewrite PA squared minus PD squared equals PA times PB, if we rewrite that, that's the same as saying that that's the same as saying that AP times AB is PD squared. That's interesting. So wait a sec. I think that probably, yeah, I'm saying if we added PA squared to both sides of that equation and then we rewrite it, it's the same as saying that AP times AB is AB squared. Let me try something.
Actually, it cannot be true. We have to prove that AX squared equals to AP multiplied by AB.
Exactly, yeah. So that's the same as showing some similar triangles, right? That's the same as saying that angle AXP is equal to angle XBA. At least I think so. Yeah. So we want to show angle AXP is equal to angle XBA, or just somehow show those triangles are similar. But AXP is kind of hard to compute. Yeah. let's see, we have kind of a, let me see what happens if I draw this circle. Maybe we could use like the radical axis theorem or something. So P would basically be the radical center of those three circles, right? So AP times AB is also the power of P with respect to this circle through D, right? So we could try to show that P lies on the radical axis of these two circles. Not sure how helpful that would be, but I don't know, maybe it would be. So we want to show that, because wait, so PD is equal to AX. So we want to show, let me do the algebra here. If we want to show P has the same power with respect to these two circles, that's the same as saying AB squared minus PD squared is equal to PD squared minus PA squared. So that means that PA squared plus AD squared equals 2PD squared. That almost means the angles of this are determined, I think. Wait, so PA squared plus AD squared is 2PD squared? That's weird. Let me try something here. Something is weird. Huh. Squared. Maybe it does. So yeah, I think exactly. Yeah. So that equation, does it just come from right triangles? Maybe it's obvious. BA squared minus PD squared equals PD squared minus PA squared. Is that obvious? Maybe it is. Maybe it's just Pythagorean theorem. I'm not sure. So let me do some algebra here. I'm just doing it on my paper. So PA squared minus PB squared, PP squared minus PE squared. So PA squared minus BP squared is equal to AE squared minus PE squared, which is BE squared minus PE squared. I'm just doing a bunch of stuff on paper.
Maybe we can try cosine law because that contains a term with BA square minus PA square.
BA squared minus what?
I am saying that cosine law contains terms like side squares difference.
Yeah. I think it might just be the Pythagorean theorem, though. That's the thing. So, hold on a sec. It's not just the Pythagorean theorem. Okay.
Now, PD equals to AX means there should be a center of rotation which takes AX to PD. If I remember something, one of them is a center.
Takes AX to BD. 2 times PA times AE is equal to PD squared. So that's the same as saying AP times AB is equal to PD squared. But but I think that's what we were trying to show in the first place. Yeah. Yeah, maybe we could try, the cosine law. I'm just trying to think. If you can figure it out, write it out in the chat.
That simply means that DPO is 90 degrees.
DP what?
If we are saying that AP times PB is equal to PD square,
Yeah.
then that means that power of P is equal to PD square. And power of P is defined as OD square minus OP square.
Mm-hmm.
Which means that triangle DPO is right angle.
Okay. Interesting.
Yeah.
Oh, but it's not. So we must have. Yeah. I guess we're saying that AP times AB. So not AP times PB, but AP times AB is PD squared.
Okay.
That's all right. Yeah, it feels like we have to be close here. So PD squared minus P. We want PD squared minus PA squared. We could also try to use that angle ADC. It's 90. I don't know if that helps. I wonder. No, that's not perpendicular. Yes. AE squared minus, we want to show AE squared minus PE squared is equal to PD squared minus PA squared. This, okay, I'm just going to try to bash it. I think this should be like bashable.
Well, actually, this is bashable with coordinates because there is a prominent right angle, and I actually found the coordinate solution.
Oh, you found a coordinate solution?
Yeah.
Yeah.
I think the product we are trying to find the AP times AB.
Mm-hmm.
We can try reflecting something in, because C is the circle, we can just extend PB to meet the circle with the radius CD.
Okay, hold on just a second. So extend BD to meet the circle at another point, I think is what you're saying.
No, extend AB.
Oh, AB.
Yeah, this one. Yeah.
Okay.
That meets somewhere at Q, and we know that P is the reflection of Q.
Yeah, okay. So I'm going to call it Q for now.
And here maybe we want to show that, or maybe we know that AD square is equal to AP times AQ.
Okay, so AP times AQ, that's like twice the product we want, and that would be AC squared minus CD squared, which is just
that's AD square.
Yeah.
Yeah.
Okay.
So AD is into this big circle.
So then AD is tangent. Oh,
maybe now we are close.
It's kind of obvious that AD is tangent, though. We don't even need that because ADC is a right angle. He's the center. But I don't know, maybe it's still helpful because we wanted to show, let's see. Yeah, hold on, this has to be bashable. Let me see. So without like, so we want to show AP squared plus AD squared is 2PD squared. PD squared, yeah, how do we, or yeah, let me rewrite some stuff. So P squared minus PA squared. We want to show PA squared minus AE squared, or PA squared plus AE squared. Minus PE squared.
I think I got a synthetic solution, but that's lengthy. But yeah, that it's a proper synthetic solution. What I did was it's a synthetic solution. I constructed the parallelogram AP KD.
APKD. All right, sounds good.
K is on the other side of D than X is. No, not this one. AD is one of the parallel sides. Such that DP is a diagonal.
Okay. Oh, APKD. I see. So let me do it this way. So I'm going to reflect A across the midpoint of D. There we go. So this is K, right?
Yeah, and the result I want to show in first conclusion that I draw from this is that AK square is equal to AP times AB.
Okay, AK squared is AP times AB.
Yeah, that would imply AD square equal to AP times AB. Wait a second. That would imply DP square equal to AP times AB. That's what we want to prove.
Okay.
And yeah, for proving this, I observed that KPB is directly congruent to DBQ.
KPB and DBQ. Or KPB and what was the other one?
KPB and wait a minute. KP equals to AD equals to DB. Give me a minute. I would just write it up and show it.
All right, no problem. Yeah, so it looks almost like this is an isosceles trapezoid, right? Yeah, I think what AML is going at is PDKB is an isosceles trapezoid. So PD equals KB, PD is equal to AX.
I think constructing the K on the other side, the way we were constructing before, would be the right way.
Oh, put the K on this side?
Yeah.
Okay.
Yeah, the reasoning included that AX equal to AK.
All right. Hold on.
The
just a sec.
problem is that I have reversed the order of A and B the way you have taken.
Ah, okay. That's not a problem. So,
Yeah, let's move the diagram a little.
okay. Hold on just a sec. So, sorry. So this is K right here. Right.
Yeah, that was K and the point X was what it was before.
Oh, wait a sec. Oh, my bad. This should be this is X. P prime should be K. Is it obvious that it lies on oh yeah, it is obvious because PD is, yeah, okay. So it lies on this circle, point K.
Yeah, and now I would prove that AK square equal to AP times PB, and for that I would show that angle AKP is KBP.
AKP is K. Let's see. So
Yeah, and I would find some congruent triangle to prove this.
okay.
I think I had my changes. Equals this.
So yeah, is AKP congruent to ABK? Might be. I'm sorry, similar. Yeah. So basically AKP is KPD, and we want to show that's KBP. I don't think KX and B are collinear, but it would, no.
Can we draw the circumcircle of KPB once?
KPB or of which?
KPB.
This?
Yeah, it's tangent to AK.
Okay. Yeah. Yeah, we want to show it's tangent to AK. So let's see.
Is KB parallel to something?
KB, maybe it's parallel to EF.
BK parallel to QD maybe. Wait, no, something should be parallel that we can chase down the angle. Maybe it's parallel to CF.
CE.
CF,
Mm,
the midpoint.
that looks like it might be true. Let's see. I'm not sure though, because it looks, no.
Oh, I have messed up my chase.
All right. Yeah, I know I have too much stuff going on in this figure. Let me delete some stuff. Maybe I'll delete this. Well, I kind of like it because K lies on the circle, so I'm not going to delete that. But maybe I'll just leave it as it is. See. Yeah, it's actually a fairly simple configuration. There has to be a way, let's see. Give me just a second. BA squared So yeah, I
Is
mean, but
AK is AKDB a parallel cyclic isosceles trapezoid?
what's this K? AKDP?
AKDB.
Oh, AKDB. I don't think it's an
That,
isometric trapezoid. It doesn't
yeah.
look like it.
Maybe the point of intersection of AB and CD, that one is the point.
A, B, and CD to this point.
Yeah, this point.
So yeah, that looks like it could be.
Yeah, that would be trapezoid because DP is equal to that because D lies on the angle bisector. This is simply the reflection.
Okay. So AKDG is a trapezoid.
Yeah.
And I'm pretty sure that's true. I just have to check if it's cyclic. But it's trivia. Oh no, so close. Almost. Yeah. But so yeah, there's a theorem about a parallelogram where the sum of the squares of the sides is equal to the sum of the squares of the diagonals. So we have 2 times AP squared plus PB squared is equal to AB squared plus PK squared. I don't know if that helps, but it looks very like related to a lot of other stuff. So wait, do we want to show PK squared? I'm getting that PK squared is 3AD squared. So PK is AD root 3. That would be weird. So that means that AF over FP is the square root of 3. Is that really true?
Is KD equal to EG, or is the diagram just like that?
Oh, KD equal to EG. It could be. I don't know if that looks like a parallelogram. Well, I could use the compass tool to check.
There is a measure tool here too.
Yeah, there's also a measure tool. But yeah, I don't think they're equal. So yeah, 2.1, 2.6.
And how about KE and DG? They should be equal.
KE and DG?
Yeah.
Yeah.
Oh.
But it's tricky. Let me erase a bunch of steps. So basically, I'll erase that. All we want to do is show that P has the same power with respect to those two circles, right?
We reduce the problem to PD and A, and all we have to do is to prove PD square equals AP times AB.
Yeah.
I think so. We can maybe remove XY and try looking at just APDB.
Hold on a sec. So we know that, yeah, we know ADP is tangent. We know that AD is tangent. Yeah, we don't really need points X and Y, right? We just need to show that the powers are the same, right? So, I mean,
We can delete the parallelogram too and
yeah.
things.
This has
That
to
circle,
have,
yeah, that circle through it.
yeah.
Though we can use the fact that AD is tangent to PDB.
Yeah.
PDQ.
Yeah. So AD squared is twice AP times, or so I wonder. So AD squared is BD squared. Maybe that helps, right?
There is a solution from trigonometry.
Oh, you have a trig solution?
Yeah.
Write it out in the chat.
It will be hard.
Sorry.
I can write the sketch. Okay, I will write it.
Okay. P times PB is equal to Oh, but wait, no, actually, what am I doing? We want to, oh no, wait, I think maybe we do want points X and Y. Well, yeah, no, we don't need. Any problem with a diagram this simple has to have a, yeah. So we just want to show AP times PB is PD squared minus AP squared. Or that's OP, OA squared minus OP squared.
I think this is just simple trig.
Yeah, okay, so DC.
Assume BAC to be theta and it just simplifies.
All right, let me look at what Serdar wrote. So DCP is 2x and DCG is y. Then DP is 2x sine CD. I mean, anything you could do with trig, you can do with similar triangles, right? So you're kind of saying take the midpoint of DP. So DPC, so AD over DP is sine X over sine Y. Wait, BCG. Okay, so this is X, this is Y. So this is also Y. So is APD similar to CBD? No, they're different, but DCP, so if this is X, are you saying angle ADP is X? 15.8. Yeah, okay, so you're just saying angle ADP is X.
Just angle chasing.
Okay, so ADP, yeah, so okay, so you're saying that's sine X over sine Y. And then AB over AC is sine 2Y. Oh, because D is the midpoint. Ah. Okay, so you have to show AC cos 2Y equals CD. How does that follow? AC cos Y equals CD? Well, yeah.
Because ADC is right triangle and DC
Yeah.
is so.
So I guess I see why AC cos Y equals CD. I see where that's true. How does that solve
Just write AP and AB.
Okay. Let me, what if, basically, I mean, one way to do this is drop the perpendicular from P to AC. So I'm still going to try to use your idea, right? But basically, I want to show that AH is equal to PD, right? So I have the right triangle AHI, and is it similar to let me check something. No. But this angle is equal to this angle. Yeah, it's been a little while. Do you guys just want to move on to the next one? Sorry. I think we're close, but yeah, I don't know. I just want to move on to something new. All right, I'm going to move on to the next one.
Coordinate does that in 10 minutes.
Yeah, no, I'm sure. Yeah, there's probably easier ways with coordinates or something like that. Yeah, I'm just gonna move on for now though. I've never done a coordinate problem on my channel though, so I just want to keep it synthetic. Hold on one sec. Okay, so you have a triangle where AB is less than AC. D is the intersection of the perpendicular bisector of BC with AC. Okay. And then P is on arc AC of the circumcircle. So that DP is parallel to BC, right? Hey, Becca, thanks for joining. Hold on just a sec. So, all right, so M is the midpoint of the side AB. And we want to show that angle APD equals angle MPD. So, I mean, does that just mean that these triangles are similar, maybe? Let's see. Let me check my measurement. 143. Nope. But we're saying they're isogonal. APD is MPB. So there's got to be some similar triangles or something, right? So all right, so the question, yeah, where are the similar triangles? That is the question. I wonder if we let PM meet the circle, if it's a similar triangle.
We must let PD because PD is median. It's median.
Yeah, okay, yeah, it's the same as showing PD is a symmedian. So then that means BFP is similar. No, BFP isn't similar to ADP. Doesn't look like it. But I mean, So it's saying like, yeah, if we draw the tangents at A and C, then it's saying that PD passes through it, right? Let me draw the tangents.
We must extend PD, I think.
Yeah. So we're saying PD passes through this point, right? Yeah. Let's see. So we're just saying that the tangents meet at a point that's at the same distance from BC as D, and that seems like it probably isn't that hard, right?
It's trivial because if we extend PD to cut ABC, circle ABC, at some point,
Then it's the same distance.
then we can take A to D. P and G are stable. B goes to infinity. We have to prove that ABGP is a harmonic quadrilateral, and it is easy to show from C.
Okay, so yeah, we want to show that this is a harmonic quadrilateral. So yeah, I'll just delete these two lines, and it's easy to show because if you project through C onto PD, yeah, so that solves it. All right, yay! So we spent a long time on the last one, but we have a quick projected proof of this one. All right, so let PD meet the circle ABC at G. Yeah. Then we want to show AGBP is harmonic. So we can project through point C. So okay. I should make this 2 wide. Okay. So BGAP or B GP AB that cross ratio, well, I'll just say projecting through C equal to GP AB or GPD and the point of infinity is equal to GD over PD. And so that means GBPA is harmonic. And then that means that PG is a symmedian in triangle APB. So and so angle APD is angle MPB. All right. Now I will move on to the next one. It's always nice when you have a little easy one like that after a longer one. All right, so we have all right, so we have a triangle ABC. And we draw the angle bisector of angle ABC. We see where it intersects the side and the circumcircle. So it intersects the side at L and the circumcircle at W. Oops, sorry. K is the perpendicular, the foot of the perpendicular from NL onto AW. Oops, sorry. So that's point K. The circumcircle of BLC meets line CK again at P. BP and AW meet at point P, so I'm going to have to make some more room here. Oh, okay, we want to show that AW is WT. Okay, so this is point T. We want to show that W is the midpoint of AT. All right.
It looks like harmonic.
Yeah, because we want to show some the cross ratio ATW infinity is 1. If we project through B, I wonder if AB is tangent to this. No, AB is not necessarily tangent. Ooh, I like that diagram better. I'm going to keep the diagram like that. So W is the midpoint of arc AC, obviously. Well, now it almost looks like it's isosceles. Okay, so let's see. ACT equals 90. Yeah, so because AW is equal to CW. So yeah, it suffices to show angle ACT is 90 degrees. That makes sense. WA, yeah, exactly, yeah. So yeah, if we can show that that's a right angle, that's one way to do it. Let's see, maybe we could. Yeah, we have an angle bisector. Yeah, we want to use, and we know that angle ALK is 90, so it's the same as showing that KLCT is cyclic. So what's the best way to do that? We could try to use power of a point. I want to show KLCT is cyclic. We want to use that P lies on this circle somehow. So we know, yeah, we could try to show angle PKCL is angle KTL. So KCL is PCL, is PBL, is TBW. So is triangle T, let's see.
BPKA is cyclic.
BPKA is cyclic. Is that
Just angle chase.
just an angle chase? Because
BAW equals to BLC equals to BPC.
BAW is BLC. Yeah, because those two, this BLC is BPC. So yeah, so BAKP is cyclic. And then from there, I wonder if you could show KL CT is cyclic. Maybe that's just power of a point or radical axis theorem. Yeah, because or is it? No, I don't think it's that simple.
K is the Mickle point.
K is the Mickle point of what quadrilateral?
Some quadrilateral. I think there should be a Mickle point here.
Hold on just a sec. Yeah, I don't think it should be a large. So we want to show KLCT is cyclic. Which means we want to show TLW is similar to TBW. Yeah, we want to show. I think we're pretty close here. So hold on a sec. So whoops. So angle LTW 17 LBW. Yeah, we just want to show W ace or, oh, wait a sec. Yeah, I guess we know WA squared is WL times WB. I kind of went in a circle.
From angle chasing, we want to show ABP equals to CL, the bottom point, but I cannot see the point at the bottom.
Oh, this point?
Yeah.
That's point T.
We have to show ABP equals to CLT.
APB is CLT. Yeah.
Maybe it's just similar triangles, I don't know.
Feels like this, yeah. Yeah, T is defined in an interesting way. So it's where BP AW mean? Yeah, we want to show ABP is CLT, like you mentioned.
This one is hard.
Yeah, I agree.
BPK is similar to BCW.
BPK,
It's similar to BCW.
BCW. Ah,
Michael point and spiral similarity. So B is the Michael point, I guess.
okay. Yeah. So BPK is similar to BCW. That means BKW. Wait, is that true? BKWC would be cyclic. Let's see. No.
Actually, it must be right. I guess similarity is wrong, or
Yeah, because yeah, I'm a little skeptical they're similar. You said BPK is similar to BCW. Let's see. You might there's a so that's 71.6. Yeah, no, they're not similar. I almost want to let T redefine T or call T prime the intersection of the perpendicular here and AW, and then show that T prime lies on the radical axis. Let me try something. So maybe we could do something with symmedians. I don't know. I wonder if TB is a symmedian. Let's see, LTK, BTC. No. Yeah, we just have to show this is cyclic. We could try part of a point. I don't know about that. Is TPK? Oh, TPK.
Could you explain all the constructions you've made?
What?
Could you explain all the constructions you've made? Or
Oh yeah. Hey, Sai.
hey,
So yeah, I haven't done a whole lot. So yeah, you have a triangle ABC. You draw the angle bisector. It intersects AC at L and the circumcircle at W. And then you drop a perpendicular from L to AW, and it's point K. And then you draw the circumcircle BLC, and it meets the line CK at point P. And then BP meets AW at point T. The only thing I added in was this circle. So we used an angle chase to show that BAKP is cyclic. But the rest is from the problem.
yeah, thanks, got it.
Yeah. All right. Just draw this for fun. I mean, we could always draw this point right here. So we want to show that BDKT is cyclic. I don't know if that helps. That might help. Yeah, we want to show BDKT is cyclic. That's the same as showing angle DBP is angle DKA. Right, that's the same as showing BWA is WDA. Wait, that's the same as showing
AL is the angle bisector of DKP.
yeah, these are both. AL is the angle bisector of what?
AL is the angle bisector of DKP. We want to prove that.
BKD or AL
DKP.
EKP.
It's D.
Oh, DKP. I'm sorry.
Yeah.
Oh, KL. I thought you said AL. That's why I was getting confused. All right. So I wonder if we can use Brahmagupta's theorem. So basically, Brahmagupta's theorem says that KL passes through the midpoint of BC. So I could explain but yeah, KL passes through the midpoint of BC. Wait, is that true? I thought that was Brahmagupta's theorem, but maybe I'm wrong. Oh no, that's only a quadrilateral with perpendicular diagonals. Never mind. Okay. So yeah, that's the same as showing L is the midpoint. Oh, but we know that because L is the midpoint of arc CD, since BL is an angle bisector. And so since L is the midpoint of arc CD, and AT is probably parallel. So yeah, okay. I think we've got it. Wait, so I forgot what I want to show, but do you remember how showing that ends up solving the problem? So once we know KL is the angle bisector, do you know how that would finish the problem?
Then we have ABP equals to PKT.
Equals PKT is AKD.
AKD, and we proved that PKDB is a cyclic quadrilateral, and we want to show that.
Oh. PKDP, or wait. So okay, so I'm gonna start out like proving what you mentioned. So
How did you prove that KL is angle bisector?
so we know L is the midpoint of arc CD, since BL is the angle bisector of BBC. And then also we'd have to show that CD is parallel to AW. I think that's an angle chase. So
Yeah, that's an angle chase because BLC is similar to BAW.
yes. So
We solved it. Wow.
all right. So I'm gonna write. So let's write it out. So so BL bisects angle DBC. That means L is the midpoint of arc DC. And then, okay, we want to show DC is parallel to AT. So that's the same as showing that angle CDA plus DAW is 180. That's the same as saying ADC is equal to BCW, which I'm assuming is just an angle chase, right? Or it's the same. Yeah, there's a couple different ways to think about it. Okay, so we have angle BDC is BPC is BAW. All right. And that means that, yeah, that means that CD is parallel to AW. And so LK is perpendicular to AW. That means that KL bisects angle DKC. So all right. And once we know that Then we know that angles. Oh, I'm sorry, go on.
AKD equals to PKT,
Mhm.
and this equals to ABT.
ABT.
Because the cyclicity.
Oh, but we don't know yet that BDKT is cyclic, right?
No, I didn't use that. I used that AKPB is a cyclic quadrilateral.
Oh, AKPB. Okay, so we have angle AKB equals angle PKT, which is equal to angle ABP.
You have to write AKD, I think.
AK. Oh, did you
D.
mean AKD? I'm sorry. AKD, yeah, is equal to PKT, which is ABP. Okay, so
Yeah.
so that means that BDKT is cyclic. All right. And then it's just power of a point, basically, I think. So, but I never proved that BAKP is cyclic. So let me write that at the top. So that was just, wait, let me just think for a second. So that was just BAK is equal to BDC by an angle chase, which is BPC. I think that's how we proved it. But let me see if there's okay, BPC is BDC. Yeah, actually, let me add the steps. So if BPC is BAW, yeah, this actually proves two things. So this implies CD is parallel to AW and BAPK is cyclic, right? Oh no, because we assumed it was cyclic in saying that BPC is BAW. Okay, so how do we show? I'm trying to remember how we did it. I don't think it was. So we just want to
AK equals to BLC.
BLC. So BAK. I think now I remember. BAK was BAW, which is BLC. So that means BAKP is cyclic. Okay. And we know BAK is or we know BAW is BLC because those triangles are similar.
BLC equals to BPC. You must write that too.
Oh yeah, equals angle BPC. And even before this, we use the fact that BAW is similar to BLC by using an angle chase. That's very easy to see. So, all right. So, and then once we know that BDKT is cyclic, then now it's just power of a point because I thought it was.
ADAB equals to ALAC, and ADAB equals to AKAT.
Hold on just a sec. So is AK times AT is AD times AB, which is AL times AC. That's right. So is that AD times AB, which is AL times AC. So that means that KLCT is cyclic. All right. And then that means that angle LCT is 180 minus angle LKT. Is 90. And so once we know that that's true, then since WA is equal to WC, I'll just say this, WA equals WC and angle ACT equals 90 implies AW equals WT. All right, thanks for your help there. That was a fun one. And I will move on to the next one. Oh, this one's kind of interesting. So we have a triangle ABC where AB is less than AC. D is the foot of the altitude from A. Okay, so we have a problem with centroids now. I don't do centroids that often on my channel, but I should do them more. So we draw the centroids. So there are in Q. So this one is R, and that one is Q. Okay. So we have all these midpoints, right? We could draw that too. F, E, and G are linear and parallel. And RQ is also parallel to BC because they're both 2/3 of the way. Okay, let P be a point on BC. So P, Q, R, and D are cyclic. So basically that would make an isosceles trapezoid. This problem is feeling easy. So P, yeah, it makes an isosceles trapezoid with D, Q, and R. We want to show that AP, BQ, and CR are concurrent. Interesting. So it kind of feels bashable. I don't know if there's a...
There exists a solution from Menelaus and Seva, obviously, I think.
Yeah. So if we know this is an isosceles trapezoid, yeah, do we want to use Cheva on the whole triangle and let, or do we want to use Cheva? Yeah.
We will let BQ intersect AC and we will use Menelaus to find the
Yeah.
ratio.
Yeah, because we know AQ over QI, so
Yeah.
and BI over IC. So, well, maybe it's not that easy because, like, we know AQ over QI, but BI over IC So we know ID is equal to IC, but there's still, yeah, maybe a bunch of stuff would probably cancel if we did that calculation. So, but yeah, I'll just draw on those for now. I wonder if let me try this. No, it's not an angle bisector. Or we could try using Desargues. So A, B, C, and P. So we want to show that A, B, C, and PQR are perspective. I think that means they're similar, right? Maybe. I'm not 100% sure. But I think it might actually be, yeah. So triangle PQR is congruent to DQR, and DQR, is it easy to show it's similar to ABC? So that's the same as saying that, so FDB is isosceles and GDC is isosceles. So it's easy to see from that DQR is similar to ABC and DQR is congruent to PQR. So I think PQ is parallel to AB and PR is parallel to AC. And then by Desargues, that would solve it. So yeah, okay. So yeah, that solves it. So yeah, you could just use Desargues' theorem. You don't even need Cheba. I don't know if I've ever used Desargues on a live stream, so this will be fun. Let's see. So yeah, I don't even think I needed point E really. Whoops. Didn't want that to happen. Let me just hide point E and that. Okay. So in fact, did I even need this? In fact, I think the problem is true more generally. Well, okay, yeah, I needed that QR is parallel to BC. Okay, and I needed that. So yeah, I don't need points J and K. It is fun removing lots of stuff in the figure. Okay. So let F, G, H, and I be the midpoints of AB, AC, BD, and BC. Okay. So AR over RH equals 2. Whoops. AQ over QI is 2. So that means that RQ is parallel to BC. Whoops. Gotta add in some dollar signs here. And then FBD and GDC are isosceles. So from there, we have some angle chasing. So yeah, let me write above this that RDPQ is an isosceles trapezoid. All right. So since those are both isosceles, we can take advantage of that. So we have basically angle QPI is equal to angle RDB, which is equal to angle ABC. And that means that QP is parallel to AB. And then similarly, RP is parallel to AC. So if you look at triangles PQR and ABC, so in triangles PQR and ABC, corresponding sides are parallel. And meet at the point at infinity. So that means we can apply Desargues' theorem. I don't even know if you need Desargues or just something about homotheties, but like maybe it's just like they're similar, so there has to be a homothety. I don't know exactly, but anyways, Desargues works. So by Desargues' theorem, A, P, B, Q, and C are all right. That was a fun one. I'm kind of glad we avoided Cheva, but even if we had to use Cheva, it's not so bad. And I will move on to the next one. Make sense? All right.